Hello everybody, we will continue our lecture in this optimal control course, and then this particular lecture will talk about linear quadratic regulator, and then subsequent 2-3 lectures also will keep on talking about this. There are several reasons for that, and as you see in the previous couple of lectures, these are computationally complex problems in general. Any optimal control formulation leads to these 2-point boundary value problems and all that. So, that requires a lot of numerical intensive procedures and all. So, then the early 50s and 60s people started thinking that is there any class of problems for which we do not really need all those kind of numerical techniques, and we can get solutions in rather computationally efficient way, even though it is limited to a class of problems actually. So, that leads to this definition of linear quadratic regulator problems, and extensively studied and extensively utilized as well. It is one of the very popular tricks of optimal control or class of optimal control problem that is found in usage in industry as well actually. So, we will see that and then proceed further some of these extension proofs and things like that in the subsequent lectures actually. So, let us understand what is this LQR problem, and then furthermore will be subsequent lectures anyway. So, generic optimal control problem, as I discussed many times before, this is what it is. J takes the form of some phi, this is terminal penalty plus some path penalty sort of thing, and then along with that there is a path constraint which is a system dynamic equation as well as boundary conditions actually. Okay. And we will consider typically this XTF is free, X of TF, but some problems it can be hard constraint also basically. Okay. Alright, anyway, so this particular LQR problem does not talk about a generic formulation anymore. Thus, it talks about a specific form of cost function and a specific form of system dynamics. Okay. So, this problem can be defined this way. The objective is to drive the state of a linear, or many times the linear is nothing but a linearized system anyway, we know that. So, the objective is to drive the state x of a linear system, okay, given by this equation to the origin, that means x of TF has to be 0 0. Okay. So, how do you do that? It can be done by minimizing the following quadratic performance index actually. Okay. So, this is the terminal penalty XF transpose SFXF, okay, and this is the path penalty, okay, where we want to maintain the state deviation small as possible throughout, and we want to maintain the control as well. We want to use as much less control as possible, and in general this x and u are nothing but delta x and delta u. Remember that when we talk about linear system, the x is not really the true state, it is the deviation state, and u is not really the true control either, it is actually the deviation control. Okay. So, what we want to minimize is deviation of the state should remain close to 0, and deviation of control should also remain close to 0. That is the whole problem actually. Okay. There are certain necessities as well, and this has to be ultimately a meaningful performance index to be minimized. So, for that we need this SF and Q, these two matrices has to be positive semi definite, and this R matrix has to be positive definite. Okay. And not only that, there are some one or two other conditions as well, we will talk in a couple of minutes later. So, just remember that SF and Q are positive semi definite and R has to be positive definite. Okay. So, that how do you select this matrices now actually? Okay. The question is, okay, we are talking about selection of a matrix, because these are the tuning parameters for the LQR design approach. So, how do you select these matrices? And one of the ways to select is just to select these as diagonal matrices, and that is what most of the time it is used that way. Okay. So, and once you select any matrix as diagonal matrix, the diagonal elements are nothing but eigenvalues. So, if you just put positive elements in the diagonal matrices, it will give you positive definite matrix actually. Okay. So, that is the trick that people play, and that to select diagonal matrices with positive entries actually. Now, even in positive entries, how will you select the entries itself actually? Okay. So, that is what I am talking. This for example, Q, whatever Q you are talking here, okay, Q is nothing but something like a diagonal matrix with Qi, okay, everything else is 0. Now, how will you select this Qi? Okay. So, the guideline here, okay, is recommended guideline turns out that, okay, you expect a maximum deviation, okay, maximum expected or acceptable value of this value actually, okay, 1 by xi square. Qy is equal to maximum expected value of 1 by xi square. Okay. Or similarly, Ri is maximum expected value or maximum acceptable value of 1 by u square. In other words, if you do that, remember these functions are nothing but u1 square r1 times u1 square r1 plus u2 times r2 like that actually. So, what it happens here is some sort of a normalization actually. Okay. So, you are talking about something like u1 square divided by u1 max square plus u2 square. Okay. This expression what you are looking at, this particular thing in that selection what I just talked of, this will turn out to be something like u1 square divided by u1 max square, okay, plus u2 square divided by u2 max square, like that. Okay. So, that means this is some sort of a normalization actually. Similarly, you are talking about doing similar operation here, a similar operation here as well actually. Okay. So, that is what I want to tell actually by doing this. There are some other some other facts to remember. I told you that this pair AV obviously needs to be controllable. The very idea of controllability is always there, and if the pair AV is not controllable, LQR control cannot be done. In fact, any other control cannot be done either actually. Okay. So, the very fundamental requirement is AB needs to be controllable, and also it turns out that A and square root of Q also needs to be detectable. Okay. So, these are all theoretical requirements. Some of you who want to know, you can pick up a LQR related book, linear quadratic books are available. Anderson and Moore is probably one of the standard books people follow actually, and see some of the proofs, reasons for that and things like that way. Anyway, so this pair AB needs to be controllable and the pair A and square root of Q needs to be detectable. Okay. And remember, as long as a matrix is positive semi definite, you can talk about square root of Q. Okay, this is computable actually. Okay. Alright, so this is the first thing, and this we already talked, and by default it is assumed that TF tends to infinity. In general, it can be finite time LQR, but if somebody does not tell you that it is a finite time LQR, just simply tells okay, it is LQR problem, then by default it is assumed that TF goes to infinity actually. Okay. And also remember that constraint problems, that means problems with state and control inequality constraints are not considered here. We will consider them later, okay, but not here right now. Okay. So, with these things in mind, let us proceed further actually. So, what is our performance index? This is going to be our performance index, half of this plus integral of T naught to Tf, half of this quantity. Okay. So, essentially in our generic framework, this happens to be our phi and this happens to be our L actually. Okay. So, path constraint is a linear equation x dot equal to x plus vu, and boundary condition given by like this actually. Okay. So, what is our terminal penalty? Phi of xf is like this. Okay. What is our Hamiltonian? Hamiltonian is nothing but L plus lambda transpose f, and remember this is our f. Okay. This is our f of xu. Okay, not small u here. Okay. Big U. Okay. Well, in our notation, any small thing is a scalar and any big thing is a vector. So, just be careful about that. We are talking about vector variables in general actually. Okay. So, this is our phi, this is our L and this is our f, and these are the conditions that are available to us actually. Okay. Alright. So, this is phi, this is our Hamiltonian L, okay, L coming from here, okay, plus lambda transpose f, f is this, okay, x plus bu. So, this is what it is. Once you know a Hamiltonian and a phi, necessary conditions are all there with us. The state equation is already there, x dot equal to x plus bu, lambda dot equal to minus del h by del x. So, it is happens to be minus of qx plus a transpose lambda. Okay. And optimal control equation is del h by del e equal to 0. So, that means u equal to minus r inverse v transpose lambda. Okay. Because you can see this, okay, from here. Let me do this. Okay. Anyways, let me quickly do this. Hamiltonian is nothing but, okay, well, we can do this. Okay. Alright. So, Hamiltonian is nothing but our half of x transpose q x plus u transpose r u L plus lambda transpose f. F is nothing but a x plus b u. Okay. Again this problem. Okay. Okay. So, this cost function this co-state equation lambda dot equal to minus del s by del x. So, if you have this h coming here, this is minus of del s by del x, one term comes from here which is q x, okay, and the other term comes from here, okay, this is lambda transpose a x. Okay. So, this lambda transpose a x, okay, that I can talk about to derivative a transpose lambda basically. Okay. And similarly, if I talk del h by del u, okay, del h by del u is nothing but one term comes from this half u transpose r u. So, that is r u plus the other term is lambda transpose b u. So, that means if I take derivative it becomes b transpose lambda. Okay. So, then this has to be equal to 0, that means you can solve u equal to minus r inverse b transpose lambda. Okay. So, that is how it comes, this optimal control equation, and this is how your co-state equation comes actually. Okay. Alright. So, this is what has been done here. Okay. Alright. So, x dot equal to x plus b u, lambda dot equal to minus q x plus a transpose lambda, and this equation del s by del e equal to 0 gives us this u equal to minus r inverse b transpose lambda actually. The boundary condition, this is, remember, this is our terminal penalty, del phi by del x f will turn out to be s f into x f. Okay. So, this is how it is. So, all these conditions starting from here, this condition needs to be satisfied for our control solution actually. Okay. Now, here is the trick in this particular problem. This lambda of t is guessed as some time varying matrix p of t into x of t. Okay. And there are justifications for that actually. Okay. One intuitive engineering justification comes from here, that lambda f is nothing but s f x f, that means lambda f is a linear function of x f. So, if at final time t f lambda f is a linear function of x f, then how about guessing that every point of time it is also a linear function of x? The motivation comes from there. There also, if you think a little bit, and then this LQR problems has a unique solution. And so, if you are able to assume something like this lambda of t equal to p t times x t and finally get a solution, then that has to be the only solution, because it has uniqueness property actually. Okay. But even going a little more further, it has been formally proven from function analysis theory, okay, of non-linear space and all that lambda of t acts in the dual space of x actually. Okay. And hence, it has to be a linear functional of that. Okay. So, we do not talk about too much on that, but somebody is interested, he can always see this classic book, a very good book actually, optimization by vector space methods. If you see that, some of these are proofs and all that will be available. But very engineering intuitive sense, it happens at the final time. So, we can assume that it can happen at every point of time from t naught to t f, and because LQR admits an uniqueness of the theorem. Okay. So, if at all we are getting a solution, that has to be the only solution actually. Okay. The solution form can differ, somebody can write in a different symbolic sense and different math sense and all that. So, it is something like sin theta equal to cosine of pi by 2 minus theta. So, it both are similar basically. Okay. You can, the expression appears to be different, but ultimately they are same actually. Anyway, so this is what it is. So, with that justification, lambda is assumed to be some time varying matrix p times x of t actually. Okay. So, this is what it is. Then with respect to that selection, let us analyze let us try to use all these equations that we have actually. So, now lambda of t is pt x t. So, what is lambda dot? Lambda dot is p dot times x plus p times x dot. And again I emphasize, do not exchange this multiplication sequence. Sequence is important here actually. So, lambda dot is p dot times x plus p times x dot. Okay. So, let us keep this p dot times x, do not change it, okay, just keep it like that. But x dot, we know that it is nothing but state equation. So, we put x plus b u, that is the state equation. U we just derived that u is nothing but r inverse b transpose lambda. So, we will put that here r inverse b transpose lambda. Okay. and then we lambda again we know it is nothing but p times x. So, we will put p times x here. Okay. Now, what is lambda of t? Okay. What is lambda dot of t? Lambda dot of t is nothing but this co-state equation minus q x term minus q x plus A transpose lambda. So, we will put that minus q x plus A transpose lambda, and lambda is again p times x, that is put here actually. So, this side of the story is co-state equation, here we use state equation, and here is optimal control equation actually. Okay. So, state equation getting used here, okay. Co-state equation getting used here, okay, this side of the story, and then optimal control equation is used here actually. So, all the three equations are embedded here actually. Okay. Now, once you have it something like that, it is all in some equation like this, you can take everything into the left hand side and make it something a big matrix times x equal to 0, and remember x is not necessarily equal to 0 basically. Okay. X is a trajectory which evolves with time, and x in general is not 0, but this equation has to be true. So, in that sense, and it has to be true for all possible values of x, that is that is also a requirement actually. Okay. If it is valid for all possible values of x, then the coefficient has to go to 0, and then that is how we will get it, the Riccati equation actually. Okay. This is famously called as Riccati equation. Italian mathematician who kind of developed this, I mean came across this equation in a scalar variable sense for the first time actually. Okay. So, that is how it is renamed as Riccati equation actually. Anyway, so this is popularly known as the differential Riccati equation, and if you remember this, there is a p dot here. Okay. So, obviously, we need a boundary condition for p also, and this boundary condition is obtained like this, because we know lambda f equal to s f x f, right. This lambda f, okay, is nothing but s f x f. But what is lambda f? Lambda f is nothing but p of t f into x of t f from here. So, you put that p of t f into x of t f or x f equal to s f x f. So, again x f is free, x f is not 0. So, hence these two is to be equal actually. So, we get a differential equation, okay, matrix differential equation with a corresponding boundary condition at T f actually. Okay. So, now what is the beauty here? This problem, if you just see this equation and this boundary condition, they are independent of the problem definition. Okay. So, we do not really bother about which initial condition the problem operates and things like that. We simply start with this boundary condition and integrate this differential equation backward, and store these values of p of t from t naught to t f, and then start using, I mean whenever the operation time starts at t naught. So, we have available solution ready of, because p of t and x of t are available, okay, your lambda is available, and hence once lambda is available, your control is also available. Okay. So, that is how the things proceed actually. Okay. So, this is what is written here. You use the boundary condition, okay, and integrate the Riccati equation backward from t f to t naught, store the solution history of the Riccati matrix from t naught to t f, and compute the optimal control online actually. Okay. When online you have to compute it, E equal to minus R inverse B transpose lambda, lambda is nothing but P times X. So, this part of the thing you can think about something like a gain matrix, okay, you can, hence you can write U equal to minus K times X actually. Okay. So, that is how it is computed. Now, the question is, do we really need to do this, because this is a differential matrix equation and all that. So, it may not be very good to do that always. So, is there a simplified way of doing that? You do not have to keep on integrating, storing and things like that actually. Now, it turns out that this great theorem by Kalman again has simplified the life quite a lot, and that is what is shown, that when T f goes to infinity and you have selected, if somebody selects a constant Q and R matrix, okay, they are not time varying matrices, then P dot goes to 0 for all time from beginning to end actually. Okay. That means, from P dot remains 0 throughout actually, it does not change, essentially the P turns out to be a constant matrix actually. Okay. If P is a constant matrix, then P dot is 0, and so if P dot is 0, suddenly this differential equation turns out to be a algebraic equation actually. And that is what is very popular in industry and everywhere actually. So, that is the reason why if nobody tells T f, then we, by default we assume T f tends to infinity actually. So, we can keep on using this as long as we wish. Anyway, so when T f goes to infinity, okay, P dot goes to 0, and hence this differential Riccati equation turns out to be an algebraic Riccati equation actually. Yeah. But remember that ARE or algebraic Riccati equation is still a nonlinear equation for the Riccati matrix. Okay. and hence it is not very straightforward to solve. It is not like by the way, there is somebody a little bit clever can see that if this nonlinear term is not there, this P A B R inverse V transpose P, that is not there, then this is nothing but a Lyapunov equation, a linear equation actually. Okay. So, that can be solved extremely easily, but in general here, okay, this is a nonlinear equation, okay, and it is not that straightforward actually. So, but what happened is, because this equation is so I mean it keeps on appearing in a number of problems throughout across the field. People have done a lot of research on that, how to come up with efficient numerical methods actually. Okay. So, it is all available now, and some of these has also gone into some routines of this control systems toolbox in MATLAB actually. So, if you just use ARE, that is algebraic recurrent equation, there is a command called ARE, there are commands for LQR also, LQR, LQR2, then discrete LQR, DLQR, ARE is available for algebraic recurrent equation. Okay. So, things like that, there are a bunch of functions available in MATLAB also actually. Okay. So, ARE is still a nonlinear equation for Riccati matrix, hence but the question, I mean the point here is, it has drawn quite a bit of attention, and hence good solution techniques are available for this actually. Okay. But also remember that a positive definite solution for Riccati matrix is needed to obtain a stabilizing controller. Okay. So, you can prove that also, okay, that with a positive definite P, lot of good things do happen actually. Because remember why, because this is a nonlinear equation, it can admit multiple solution actually. So, you have to discard all of the solution and take one solution which is positive definite actually. Then you get lot of good things there actually. Before going to further things, which we will do it in next class anyway, I thought in this class we will see some example problem which will clarify our ideas in a good way actually. So, the first problem that I really want people, all of you, to kind of put your hands on is a very standard classical benchmark problem of stabilization of inverted pendulum. Okay. And inverted pendulum are very intuitive these problems. There are a variety of inverted pendulum problems available, and in this problem what we are talking here is there is an inverted pendulum on a cart actually. Okay. There is a cart and there is an inverted pendulum, and one way to stabilize that is to move the cart. Okay. But one way to stabilize them is also to apply a torque around that. Okay. So, by moving the cart here and there, you are also indirectly applying a torque actually, but in general you can also directly mechanize some sort of a motor or something like that, where this torque can be generated actually. Okay. So, the system dynamics, okay, this inverted pendulum has also drawn a little more interest in aerospace community, because when the launch vehicle is launched vertically, okay, and that point of time it happens to be a kind of an inverted pendulum actually. Okay. It is not that the string has 0 mass, the entire length will have distributed mass and all that actually, that is a different issue, but ultimately the payload will be there at the top. Okay. And the instrumentation and fuel pump, fuel tank and everything will be towards the, towards the top actually. So, hence you will consider that as some sort of an inverted pendulum actually. Okay. So, anyway, so these are some of the motivations why this inverted pendulum problem is studied a little bit in depth actually. Alright, so the system dynamics, you can derive it using this Newton's law of motion and all that, but after you do all that, the dynamics turns out to be something like this in a linearized form. Okay. So, in a linearized form, if you take theta, the deflection from vertical axis is what you want to minimize anyway. So, if you do this moment equation and all that, then it turns out the theta double dot is nothing but g over L into theta, okay, plus u or minus u. If u is in the opposite direction, then it is minus u actually. Okay. So, that is u is the control variable and theta is the state equation. This is a system dynamics. So, theta and theta dot happens to be the state variable actually. So, we write it that way, the state space form. First we write it this dynamics in state space form, where you define x1 is theta and x2 is theta dot. Okay. So, we put that in x1 dot and x2 dot, and then remember this dynamics has to be written. So, it takes this form actually, x1 dot which is x2. Okay. So, x1 dot is 0 times x1 plus x2 plus 0 times u. So, x1 dot is x2, whereas x2 dot is theta double dot, which is nothing but that. So, x2 dot is omega n square into x1 coming from here plus 0 times x2, but minus 1 times u basically. Okay. That is how we get this A, B matrices and all. And these have to be constant matrices, they are constant matrices actually. Okay. Now, what is our objective? Our objective is to minimize the performance index like this. Why? Because we want to minimize theta. Okay, it has to remain vertical. So, we want to minimize the theta deviation. Okay, with minimum application of control as well actually. Okay, and in this particular problem we write it this way. So, this r equal to 1 over c square and q happens to be 1 here because the theta is the x1. So, the 1 here and 0 everywhere else actually. Okay. And somebody can also think about minimizing theta dot as well. Okay. But there are problems, there are good things and bad things about that. Theta dot minimization means you can also introduce a penalty for theta dot here, that means something will appear in this diagonal element as well. Good thing about that is once it reaches the vertical point, that is a good thing to have, because you do not want theta dot to develop further. But if you minimize theta dot on the way, okay, then your response will be sluggish actually, your response will not be fast. Okay. So, if somebody is little bit clever, they can initially operate with this cost function, and once it is a very small narrow boundary, then you can switch over to the other cost function and try to apply in the other controller actually. Okay, that is a possibility. Okay. But here we are not talking about that, it is just a demonstrative problem anyway basically. Okay. So, q happens to be like this and r happens to be like this 1 over c square, and then let us see whether you can really apply our knowledge and then get some solution out of this actually. Okay. So, here is a t goes to infinity. So, this is Tf is infinity. So, we have this algebraic Riccati equation, that is what we have to bother about. So, we will put that, and this is one equation I will also recommend people taking this course should remember actually. But once you remember Riccati equation, you are remembering two equations simultaneously. You are remembering Riccati equation anyway, but you are also remembering Lyapunov equation. You take out this term and it is nothing but Lyapunov equation actually, and these two equations are very heavily appearing in many of our fields. So, I thought it is good to remember this equation actually. So, this is our algebraic Riccati equation, P A plus A transpose P minus P B R inverse B transpose P plus Q equal to 0. So, now we are interested in solving for P, okay, and we want that kind of solution which should have symmetricity as well as positive definiteness. Okay. So, let us start with that. So, we start with the symmetric matrix P2 P2, okay, and this P1, so that is P1 P2 and P2 P3 here, and then we put it back here. Okay. So, P times A, this is P and that is A, sorry, this is A. So, if you multiply this P with that A, okay, we will end up with this kind of thing matrix plus A transpose P. So, you will have this at A, okay, A times transpose times P, and remember P is a symmetric matrix. So, this happens to be just the transpose of this matrix, what you get here is nothing but the transpose of that. So, you do not have to really compute that basically. Okay. If you compute this, then immediately you can write this actually, okay, minus P B inverse P B R inverse B transpose P, and you can compute all that and then come up with that actually. Okay. P is given as this way, okay, B is given as something like this 0 minus 1, okay, P B R is given as something like this 1 over c square, okay. So, R inverse is just c square, and then B transpose and P are all available actually. So, you compute this matrix multiplication terms turns out to be like that actually, okay, plus Q, and Q is like this, okay, that is equal to 0. Okay. So, this equation turns out to be like that, and if you see now component by component, okay, here just a comment that here if somebody wants they can simply use take a value numerical values of omega n square and all that and simply use this MATLAB toolbox. Once you select a value for omega n square and c square, you can use this LQR solution and get a solution, that is not a point. But the point here is are you able to solve it using closed form solutions actually. Okay. I mean symbolic solution, that is what you are attempting for actually here. Okay. So, once you write this equation, okay, you write it in component by component. So, the first 1 1 element will give us all that, okay, that equation, 1 2 element will give us that way, and 1 3 will give us that actually. Sorry, 1 1 1 2 and 2 2, that is all we need actually, because other one will be repeated actually. The what you get from 1 2 will be same as what you get from 2 1 actually. Okay. So, that is repeated equation, you can ignore that, because we have already selected this P 2 P 2 here, remember that. So, we have only 3 free variables. So, we need 3 equations only. So, even if one equation is repeated, we are not bothered about that actually. Okay. So, using these 3 equations, you have to solve for P 1 P 2 P 3, and remember these equations are nonlinear in general. So, it can have multiple solutions and all that. Okay. So, if you use this thing, remember this is a quadratic equation in P 2. So, we know the solution for that, P 2 equal to 1 over c square, this form actually. Okay. And P 1 can be computed there. Once you know P 2 and P 3, P 1 is a direct function anyway. Okay. And this equation, if you use the third equation, you will get P 3 is nothing but plus or minus 1 by c square root of 2 P 2 from here. Okay. Right. So, what it happens, P 3 needs to be positive. So, now there is a ambiguity here, okay. And remember P 3 is a diagonal element. So, we are better off by selecting this positive element actually. I mean this P 3, okay, we talk about something like a plus or minus term. So, we will select P 3 as positive term actually. Okay. Once you take P 3 as positive term, okay, then P 2, okay, P 2 needs to be positive either actually, okay, because P 3 is square root of 2 P 2. So, unless P 2 is positive, we will end up with some sort of a imaginary number and all that actually. Okay. So, we want real values at P 3, okay, here. Okay, and if it is real values, then better that this has to be square root of P 2 and P 2 needs to be positive also basically. Okay. So, if P 2 is positive, then remember this term what you are getting is more than that. Okay. So, we are better off by selecting the positive value, not the negative sign here. Negative will be lesser than that basically, because this is nothing, this omega n fourth plus e square square root, okay, this is going to magnitude wise it is going to be greater than omega n square. So, if you select a negative quantity here, then P 2 will turn out to be negative number and things like that. Once P 2 is negative, P 3 will turn out to be imaginary quantity. So, that kind of things we will try to avoid actually. So, we will take P 2 as some positive number, and then here also we will select a positive number actually. Okay. So, this is what it will happen actually. So, this is how we will eliminate that, and P 1 as I told you can solve it, okay, but it turns out that P 1 is essentially not needed, because your gain matrix turns out to be a function of P 2 P 3 only. Control gain matrix is R inverse B transpose P. Once you compute that turns out to be like this. So, this P 1 is essentially not needed, but it is needed for only cross checking purpose or some getting a feeling for what is P 1 and all that actually. Anyway, so the control matrix can be computed that way, where P 2 is given something like this and P 3 is given something like this. Okay. So, the control is ultimately given in the form of minus kx. So, minus kx means this way. And also notice that even though we did not take this theta dot penalty here, that does not mean we do not need theta dot feedback. Theta dot feedback is here is necessary, because it is a state feedback control solution anyway. Okay. So, the way to go ahead and do that is, I mean to implement it is we need both theta and theta dot information for the controller. Okay. Alright. So, what's the good thing about that? We have done some selection and all that. So, the final question is, have you made an unstable system stable actually? That's the question there. The inverted pendulum by default is unstable anyway. Analysis will also show that is unstable actually. Okay, we will see that. So, open loop system, if you talk about an open loop eigenvalue, then your A matrix is only thing. So, if you take this A matrix and try to compute the eigenvalues, okay, lambda I minus a, which turns out to be like this, is nothing but omega lambda square minus omega n square equal to 0. So, that means lambda is nothing but plus or minus omega n. So, obviously, one root is there on the right half pole, and hence the system is unstable, and we know it very well that inverted pendulum is unstable in any case basically. Yeah. So, mathematically it conforms to that, but that is not the point, but this is open loop system anyway. The whole idea is after putting the feedback, after applying the control, is the system stable. That means we are talking about a closed loop system dynamics actually, and closed loop system dynamics is very easy to see. Okay, this okay. So, closed loop system dynamics, once you have this this x dot, okay, is equal to Ax plus Bu, Bu, and u equal to minus Kx. So, if you put that together, then x dot happens to be Ax minus Bkx. So, it is nothing but A minus Bk into x. So, this is what we are talking about as closed loop matrix actually, okay, all the time in linear systems. Okay. So, this is what you are doing here actually, A minus Bk. So, A minus Bk, because now k is available. So, we put that A is there, B is there, k is available. So, put it back, and this turns out to be like that. And for further simplicity, we can something like define omega square is something like this. Okay. So, P2 and P3 you can write in a simplified sense basically. Okay. And closed loop poles will be given by this eigenvalue equation anyway. So, we try to expand that equation now, and it turns out to be something like this, lambda square plus this quadratic function. I mean, this is a quadratic equation in terms of lambda, and this solution turns out to be like this. Okay. So, what happens here? The real part is negative actually. Okay. That means both the roots, okay, has been shifted to the negative side actually. Okay. That means if you really want to see in a picture sense, then initially the open loop poles were something like this. Okay. And what we have done by doing this is okay. So, we have shifted the poles somewhere here actually. Open loop poles were somewhere, I mean, okay, this is your sigma, okay, sigma and j omega axis. So, initially the poles were somewhere like this, and one was unstable, okay, and then these two poles got shifted to this, which both are stable actually, both are in the left hand side. Okay. So, what I am telling here is, hence the closed loop system is guaranteed to be asymptotically stable. That is the message actually. Okay. Alright. So, before stopping this lecture, we will talk about another example, which is again a very interesting example actually. Okay. And we talk about finite time problem now, and finite time, that is an infinite time problem actually. Now, we talk about finite time problem, and finite time problem, this is a very standard problem, a temperature control problem in a room, let us say. Okay. Now, the system dynamics turns out to be something like that, theta dot is minus of A into theta minus theta A plus Bu, where theta is the ambient temperature, whereas theta is the actual temperature basically. Okay. And the way to control temperature is by heat input. I mean, so we are assuming here that either heat can be given or it can be taken out, either way actually. Okay. So, if the temperature is lesser than what you desire, then you have to pump in some heat. So, you have to give some heat input. Okay. If the temperature is already over, I mean, you want to reduce the temperature, then you have to pump out some heat actually. Okay. You take out some heat actually that way. There are two ways of formulating this problem, and we will see the two ways of both the ways of doing this actually. So, the okay. Okay, first problem is case 1. Okay. We'll talk about something like a hard constraint, where theta f, final value of theta, the temperature has to be equal to 30 degree. Okay. And this case 2, we will talk about a soft constraint, okay, where the final penalty is not there here, but a hard constraint is in place. But here the final constraint is not there, but a soft constraint is in place. Right, theta f has to be as close to 30 as possible. That is what we are comfortable with, and then we will put this cost function actually. Okay. So, these two problems, system dynamics is same, objective is nearly same. One we talk about exactly 30 degree, and the other one is approximately 30 degree. and as SF goes to infinity, these two problems are same actually, it has to be same. Okay. When SF goes to infinity, okay, then theta f has to be equal to 30 degree, okay, that is the requirement actually. Okay. So, one is done in a hard constraint way, the other one is done in a soft constraint way actually. Okay. So, let us see for the solution. So, for our simplicity, we will define this something like this: theta x equal to theta minus theta a, and theta 0 happens to be theta a, right. So, that is our initial condition, the ambient temperature actually, right. Initially, the temperature is at ambient temperature. So, what is our x 0? X 0 is nothing but theta of 0 minus theta a, okay. Theta of 0 is theta a anyway, that turns out to be theta minus theta equal to 0. So, initial condition in state variable x is nothing but 0 basically, okay. And what is the system dynamics? System dynamics is like this, and theta a is a constant value, remember that. So, theta a dot is 0. So, if I do theta a dot minus here is okay. So, I am talking about x dot equal to minus a times x plus Vu, okay. This is what it is, x dot equal minus x plus Vu actually, okay. Now, Hamiltonian is nothing but case 1 what we are talking here, L plus lambda transpose f, and L plus lambda transpose f is common to both anyway, only phi is different, this is this phi and that is 0 and all that actually, okay. Anyway, so coming back, this is your Hamiltonian, which is half of u square coming from this term, plus lambda times f, f is nothing but minus x plus Vu basically, okay. So, that is coming from this this state equation here, okay. This is our Hamiltonian. So, what is our lambda dot? Lambda dot is minus del h by del x, and if you do this del h by del x from this expression, it turns out to be this one, right. Only this term will contribute actually, okay. So, del h by del x is nothing but minus a lambda, and minus of that is again plus a lambda. So, lambda dot is a times x, and here you can also when very interestingly you can see that, let us assume that a is positive, then what happens, and homogeneous system u is not there, okay, u is 0, then x dot on one side you have this okay, one side you have this x dot equal to ax, okay, and the other side you have lambda dot equal to minus x dot equal to minus ax, and lambda dot equal to ax, a lambda basically, right. So, what you are looking here is, if a is a positive number, then x is state equation is positive, stable, okay. If x is a positive number, okay, then x dot equal to minus x, that means this equation is a stable equation, whereas this equation lambda dot is a lambda, a is a positive number, and hence this is an unstable equation actually, okay. So, see that now these kind of things are available anyway. Alright, so this is what it is. But anyway, coming back, this is our state equation, this is our co-state equation, and this happens to be our control equation, okay, u equal to minus lambda. So, as long as we know minus lambda times b, so the b is known to us. So, as long as we know lambda, we are done actually, okay. So, necessary conditions to summarize happens to be like this: x dot equal to minus x plus Vu, lambda dot is a lambda, and u equal to minus v lambda. So, the solution of the first case, okay, hard constraint case, we can proceed this way. This equation happen to be kind of an independent equation here, which is a lot of good thing, because you can do closed form solutions easily now, okay. So, lambda dot is a lambda. So, with respect to lambda f, because lambda f is something that is known to us typically. So, with respect to lambda f, the solution happens to be like that: e to the power a t minus t f into lambda f, which is equal to e to the power, just to put minus sign here, t f minus t. Typically in all our missile guidance problem and all, this function appears heavily, t f minus t, which is nothing but t go basically, time to go basically. How much more time is available for our control application? So, that is the concept of time to go basically, okay. So, this lambda is nothing but e to the power minus a times t f minus t into lambda f, okay. And hence if I know my lambda, okay, my control is now known, minus b times lambda. So, minus b times lambda is there, but remember lambda f is still not known actually, Okay, so that you have to compute. Okay. Anyway, b is available, lambda is available. So, what is my x dot now? X dot is minus ax plus b times u, and u is available now. Okay. So, this expression is available. So, I put it back here. Okay. Now, this equation is nothing but a linear time invariant system with a forcing function actually. Okay. So, I can try to solve it, and one way to solve that is using this Laplace transform way of solving and all that. So, you can take a Laplace transform of this equation both sides, and one side it will be s times x of s minus x of 0 in time thing, and x of 0 is nothing but 0. Okay. So, put that 0, and right hand side is minus a times that minus b square lambda f, and this kind of thing, whatever this Laplace transform of this function actually turns out to be like that. Okay. So, you solve it, I mean take this s minus a, I mean these two terms take it to one side. So, this will turn out to be s plus a into x of s, okay, and hence you can solve it using this inverse Laplace transform ideas and all that. So, x of s turns out to be, okay, if you take it and divide it by s plus a everywhere and all that. So, this is s minus a into s plus a. S plus a will come from this term and that term one side, and then divide it by that. So, we will have s minus a into s plus a. So, that is s square minus a square sort of thing. So, you will have this term. You can again I suggest all of you to carry out this algebra yourself in pen and paper actually. Okay. So, x of s is nothing but this one, okay, and then this expression can be done in partial fraction way. You can, if you want to solve it, it is very easy rather. So, this partial fraction happens to be like this, okay, and hence you can take the inverse transform and get it that way. Okay. Now, you will be able to you will be able to your final hard constraint, and hard constraint happens to be this guy, right. Okay. This hard constraint in the state space form, in whatever state we have defined theta minus theta a, turns out to be 10 actually. Okay. So, x of t f, because x of f is now available in the closed form way, but lambda f is unknown, remember that. So, that you have to solve. We will be able to solve it using this boundary condition anyway. So, at this using this expression, put t equal to t f, and when you put t equal to t f, x of t f is nothing but 10 degrees. So, you put 10 and then you solve it from solve for lambda f from this equation. So, 10 equal to all that, and hence lambda f is turns out to be like that. So, x of t happens to be like this actually. Okay. So, we are able to actually solve a hard constraint problem, okay, using some of these simplistic ideas, and primarily the key point here to note is this lambda equation turns out to be independent equation. Okay. It is not coupled with x and all that. So, that made our life simpler actually. But the point here is, okay, using this expression, if I put x of t f, okay, that you can very clearly note that x of t f, if I put, it is nothing but e to the power t f, the numerator and denominator has the same term, this will cancel out and you will get exactly 10. Okay. That means the boundary condition is exactly met actually. Okay. Now, what is the controller? Controller expression we already have. Okay. This is our controller and all. Now, lambda f is an expression available, right. Lambda f we have solved for lambda f. So, putting that we will get a controller expression actually. So, this controller if you use for about whatever I mean t f is given, right. Okay, for t equal to t f, t 0 to t f if we apply, okay, t equal to 0 to t f if we apply that, okay, exactly we will be able to get it actually. Okay. And remember this this is a symbolic solution. So, t f is still a variable, okay, but you can use various values of t f and see this one actually. No matter what t f value you take, it will be exactly satisfied actually at that point of t f. Now, what about the case 2, which is soft constraint, that we are not bothered about that kind of control actually, okay, but we are not okay. So, what I mean there is a little bit of drawback here, okay, if you use this I mean typically when the hard constraints will have that drawback anyway. This is not I mean this particular problem it is still okay, but then in general if you have a hard constraint problem, the control requirement at the end turns out to be infinity, which is not possible to meet actually. There is a control singularity at the end, what I mean actually. Okay. Okay. Anyway, so coming back to this is a soft constraint approach. Soft constraint means we are interested in xf going to be approximately 10 degree. Okay. and then the corresponding cost function happens to be like this. Okay. So, then lambda f is nothing but del phi by del x f. So, that turns out to be something like this. So, from here you can solve for x f as something like this. Okay. But x of t we have already solved, that part of the solution remains same actually. So, we solve it like this, I mean x of t is available. Okay. Now, you can put t equal to t f and then substitute this, and then you try to solve for lambda f. T equal to t f, x will become x f is nothing but that. So, put it there, and that will become a equation in terms of lambda f actually. So, we solve for lambda f, that is what you have done here actually. Okay. Solve for the, put the two equations there and then solve for lambda f. So, what is happening here? Only the lambda f expression is different, other things are same. One case the lambda f is turns out to be like this, the other case the lambda f turns out to be, okay, we have just solved it here somewhere, okay, turns out to be like this. So, these two expressions are different actually, okay, and hence the control and everything will become different actually that way. Okay. Alright, so lambda f is like this here, and hence lambda turns out to be like this, and hence your control nothing but b lambda minus b lambda, and happens to be like that. Okay. So, the two controllers will be different depending on whether you are talking about a soft constraint or hard constraint actually. Now, the question is, if SF tends to infinity, then soft constraint is nothing but hard constraint. So, does it satisfy that actually? Okay, because the cost function, if you see, okay, if you started with that cost function, SF goes to infinity, as I told, these two problems are same. So, does it happen that way? Okay. So, we can see that in limit, when you do this limiting calculation, u of t under soft constraint when SF goes to infinity happens to be like this, and hence you can simplify this expression, you can carry out this algebra and very clearly say that some of these expressions will nullify, and ultimately you will end up with same hard constraint control actually. This expression simplifies, because 1 by SF is 0. So, this is gone, okay, and we are left out with this 2 goes to top, this is 20, and 1 b will cancel out. So, you will end up with this expression, which is nothing but the expression for the hard constraint control actually. So, the summary is, the soft constraint problem behaves like the hard constraint problem when TSF goes to infinity. So, that compatibility check is also there actually. Okay. Alright, so I think these two examples will give us some ideas that how do we handle this, both in terms of Riccati equation as well as hard constraint and soft constraint sense, things like that actually. Much more on LQR control and extensions, proofs, then all that we will talk in subsequent lectures actually. That is all I want to